Welcome to the deep dive. Today, we have a mission curated specifically for you. Imagine you're diagnosing a broken arm. You look at an x-ray and it gives you this clean binary answer.
Right, it's very straightforward.
Yeah, it's comforting. But what happens when you need to diagnose a spacecraft that's re-entering the Earth's atmosphere at over 1,000 degrees Celsius, and it's being piloted by an artificial intelligence that might actually be hallucinating?
Oh, man. I mean, you are instantly thrown into the absolute deepest, murkiest waters of extreme engineering.
Yeah.
You can't just, slap a basic thermometer on the outside of a starship and assume the data it feeds to the ship's brain hasn't been corrupted, or spoofed or manipulated by just the sheer chaos of that environment.
Exactly. And that incredibly complex scenario brings us to the core of today's deep dive. We have a really fascinating stack of recent documents in front of us today.
Yeah, some really wild stuff.
We're talking about highly technical briefs, slide decks, and non-provisional patent applications, all dated late 2025. And the crazy part is, they all trace back to a single inventor named Richard Dean Lynes.
Which is just wild in itself, right? I mean, you usually see patents of this scale coming out of these massive corporate R&D departments.
Right, places with thousands of engineers.
Exactly. But these are highly detailed, multi-million-dollar acquisition and licensing pitches aimed straight at the very top of Elon Musk's empire.
Specifically targeting SpaceX and XAI. So our mission today is to explore how this one inventor proposes solving two of the biggest, just most stubborn bottlenecks in modern tech.
Huge bottlenecks, yeah.
First, achieving rapid, commercial, aircraft-like reusability for the Starship rocket. And second, solving this massive trust deficit that is currently paralyzing enterprise AI adoption.
And ultimately, we're going to look at how these two seemingly unrelated solutions just perfectly synergize to lay the groundwork for an actual future Mars colony.
It's a lot to cover. Okay, let's unpack this.
Well, we really need to start with the physical hardware bottleneck. Because, before humanity can even think about governing advanced artificial intelligence on Mars, we have to actually get the computer hardware there in one piece.
Which is easier said than done.
Right. And right now, Starship's primary vulnerability is its thermal protection system. We're talking about the thousands of ceramic thermal tiles that just covered the belly of the ship.
Those iconic black hexagons. I mean, they're essentially passive armor. They just sit there.
Right.
Absorbing and radiating heat, taking the absolute brunt of the plasma wall during atmospheric reentry.
Yeah, but the turnaround time on those is just brutal.
Yeah, I was reading that they require anywhere from like 2 to 4 weeks of intense inspection and refurbishment between every single flight. Plus, they have these persistent gap vulnerabilities.
The gaps are a nightmare.
If a tile shifts even slightly, superheated plasma can sneak through the cracks and literally melt the steel hull underneath.
And beyond the turnaround time, they impose a massive weight penalty. The ceramic tiles and the actual load-bearing structure of the ship are two completely separate, redundant systems.
Wait, really? So you're carrying the ship plus the armor for the ship?
Exactly. You're carrying the weight of the ship plus the weight of the armor protecting it.
It's basically like gluing a fragile, shattered teacup to the outside of a bullet.
That is a great way to put it.
It's just fundamentally unsuited for rapid turnarounds. Like, you couldn't imagine landing a commercial Boeing 737 and then making the passengers wait a month while technicians re-glue the entire exterior of the fuselage before it can fly again.
No, of course not. And that is the precise argument Lynes makes in his $60 to $100 million licensing pitch to SpaceX.
So what's his alternative?
His proposal completely eliminates the tiles. He wants to replace them with the Integrated Thermal Protection System, or ITPS.
Okay, ITPS.
Yeah. This is a triple-layer active cooling system, but the brilliance is that it's integrated directly into a carbon fiber honeycomb structure. He is making the cooling system and the structural hull of the ship the exact same thing.
Okay, a triple-layer active hull. Let's break down the mechanics of how that actually survives 1,000 degrees. What is the outermost layer, the one facing the plasma?
So layer 1 is a ceramic matrix composite outer skin. But unlike the current tiles, it isn't solid.
Oh, it's hollow.
Well, it has microchannels embedded right into the material circulating a coolant, either liquid sodium or supercritical CO2. This specific layer is designed to provide 5 to 10 megawatts of cooling capacity through phase change.
Let me stop you at supercritical CO2, because that sounds like pure sci-fi jargon. A supercritical fluid isn't just a liquid or a gas, right?
Right.
It's a state of matter where it's pushed to such high pressure and temperature that the boundary between liquid and gas just disappears. So it has the density of a liquid, so it can hold a massive amount of heat, but it flows through those microchannels as easily as a gas.
Yes, that is the crucial mechanical advantage here. It absorbs the massive latent heat of reentry without boiling into these giant vapor bubbles that would just block the flow in those tiny channels.
Oh, that makes sense.
And the choice of CO2 is highly intentional for an interplanetary system. I mean, CO2 makes up 95% of the Martian atmosphere.
Oh, wow.
Yeah, you can land on Mars and literally compress the local air to refuel your spaceship's cooling system.
That is brilliant resource utilization. But I mean, 10 megawatts of cooling, even with supercritical fluids, might not be enough to stop a literal wall of plasma from degrading the skin over time. How does the rest of the heat get deflected?
Well, layer 2 handles the deflection. It sits right beneath the skin and consists of a porous silicon carbide foam. And this layer utilizes transpiration cooling.
Transpiration cooling.
Yeah, it actively pumps the coolant through the microscopic pores of the foam. So the ship is effectively sweating gas.
Sweating gas. So it's forcing a layer of relatively cool gas out of its own skin, creating this physical buffer zone that pushes the superheated atmospheric plasma away from the metal. That is wild.
It's incredible. It creates a protective film that adds another 3 to 5 megawatts of cooling.
Okay, and layer 3?
And we hit layer 3, which is the actual load-bearing structure. It's a thick carbon fiber honeycomb core. This layer handles the heaviest load, like 10 to 15 megawatts, using ram air cooling.
I imagine that uses the actual physics of falling through the atmosphere against itself. Like if you're dropping at orbital speeds, the air pressure in front of the ship is immense.
Yes, yeah.
You could theoretically channel that raw pressure to passively drive cold air through the empty hexagonal cells of the honeycomb.
You just nailed the exact aerodynamic mechanism. The structure holding the ship together doubles as a giant convective heat sink powered by the descent itself.
That is so elegant.
And the mathematical models Lynes provides for this triple-layer system are just staggering. He calculates a 44% mass reduction compared to the current tiles.
44%.
On the nose cone alone, that's dropping from 320 kilograms down to just 180 kilograms.
I mean, in aerospace engineering, shedding 44% of your mass is the difference between a struggling prototype and a complete commercial monopoly.
Oh, absolutely.
Not to mention, if this actually works, the turnaround time is slashed by 90%. You go from widths of tile inspections to just 1 to 3 days, and the lifespan of the heat shield jumps from maybe 10 to 20 flights up to over 100 flights.
It represents a total paradigm shift from passively absorbing heat to actively managing it.
I have to push back here, though.
Sure, go ahead.
Active cooling fundamentally requires pumps to move all that supercritical CO2. And the golden rule in aerospace is that adding moving parts means adding failure points. If a mechanical pump jams or a seal blows at 1500 degrees Celsius, doesn't the ship just instantly disintegrate? Aren't we just trading the fragility of ceramic tiles for the mechanical risk of a broken pump?
Well, what's fascinating here is how the ITPS accounts for exactly that catastrophic scenario. The inventor isn't relying on standard mechanical redundancy. He uses physics to guarantee backup power.
Physics.
Yeah. Lynes proposes a thermoelectric generator, or TEG, backup system. This relies entirely on the Seebeck effect.
The Seebeck effect, if I recall, that's where you take two different conductive materials, you heat one side and you freeze the other, and the sheer temperature difference forces electrons to flow from the hot side to the cold side, creating an electrical current.
That's the exact mechanism. Now picture this ship during re-entry. The outer skin is getting blasted at 1200 to 1500 degrees Celsius, while the inner honeycomb core is actively cooled down to around 200 to 400 degrees.
That is a massive thermal gradient.
Exactly. By embedding solid-state TEGs between those layers, the system generates 500 to 1,000 watts of electricity per square meter.
And because TEGs are solid state, there are absolutely no moving parts to break.
None. Zero moving parts. The hotter the ship gets, the more electricity it autonomously generates to run secondary redundant backup pumps.
So it literally harnesses the inferno that is trying to destroy it and uses that exact energy to power the systems keeping it alive.
Exactly. It runs completely independent of the ship's main power bus. If the main battery dies, the heat shield just keeps pumping.
Okay, that is an incredibly elegant workaround for mechanical failure. But we also have to talk about physical damage. Let's say structural stress creates a micro crack in the hull. A redundant pump can't fix a physical hole letting plasma inside.
True. And that brings us to the self-healing chemistry of the outer skin.
Self-healing.
Yeah, the ceramic matrix composite is embedded with boron carbide additives. If a micro crack forms during the violent vibrations of reentry, oxygen from the atmosphere rushes in, and the local temperature at the crack spikes to 1200 degrees Celsius.
Okay, and then what?
At that exact temperature threshold, the boron carbide chemically oxidizes into a highly viscous borate glass.
So the wound literally starts bleeding glass.
In a sense, yes. Through simple capillary action, the same way a paper towel sucks up water, this liquid glass is drawn directly into the microcrack.
Wow.
As soon as it fills the void, it cools and solidifies, recovering 80 to 100% of the hole's original structural strength.
It is a completely autonomous repair that uses the ambient destruction as its trigger.
Exactly.
That covers atmospheric reentry perfectly, but for a Mars mission, the ship spends 6 to 9 months coasting through deep space, which exposes it to micrometeorites traveling at like 10 kilometers per second.
Which is terrifying.
Yeah, at that speed, standard armor behaves like a liquid. Even a grain of sand hits with the kinetic energy of a hand grenade.
Standard armor is completely useless against hypervelocity impacts, which is why Lynes integrates a Whipple shield into the transit phase.
The Whipple shield.
Yeah, instead of relying on thick, heavy metal to stop the impact, it relies on spacing. The design uses an incredibly thin 1 to 2 millimeter outer bumper, followed by a 10 to 20 millimeter empty standoff gap before the main ITPS hull.
I see the logic. When a micrometeorite hits that thin outer bumper at 10 kilometers a second, it doesn't just punch a hole.
Wow.
The kinetic shockwave is so violent that the incoming particle and the bumper material instantly vaporize into a superheated plasma cloud.
Right, the particle shatters itself, and because of that empty standoff gap, that highly destructive plasma cloud has 20 millimeters of empty space to expand.
And as it expands, it dissipates its energy.
Precisely. By the time that cloud actually hits the main thermal skin, the force is spread out over a wide area and easily absorbed. It neutralizes deep space threats before they ever touch the active cooling system.
All right, so we've mapped out this incredibly robust physical framework. We have a ship that bleeds glass, sweats gas, and vaporizes meteorites. It physically cannot be destroyed.
It's a beast.
But here is the fatal flaw in any modern aerospace design. The ship's physical sensors are actively feeding telemetry data to the onboard AI to adjust those cooling pumps. What happens if that sensor data is corrupted or the AI's logic gets hacked?
Ah, right.
I mean, a physical shield is entirely useless if the AI gets confused and actively steers the ship into the Martian dirt.
Which is exactly why the narrative of these patents makes such a sudden pivot here. Lynes knows the hardware is only half the battle.
Right.
So alongside the SpaceX pitch, he has a parallel $150 to $200 million acquisition pitch explicitly for xAI, Elon Musk's artificial intelligence company.
We are moving from surviving the physical extremes of thermodynamics to surviving the ethical and legal extremes of AI data provenance.
Exactly.
And for you listening right now, this is where it intersects with your daily life. Because the fear of AI isn't just an aerospace problem, it's a massive enterprise problem. Like, if you work at a major corporation, you probably have strict policies against putting proprietary company data or client emails into an open consumer AI like ChatGPT.
Right, because you don't trust where that data goes.
Exactly.
And the statistics back that up completely. While consumer AI is booming, about 73% of enterprises refuse to deploy AI in critical workflows due to governance, privacy, and trust concerns.
That's a huge chunk of the market.
It is. Plus, upcoming regulations like the EU AI Act of 2026 are going to legally demand that AI systems be 100% auditable. If Musk's AI model, Grok, isn't enterprise-ready, it gets locked out of a multi-billion-dollar commercial market.
Right. The current AI ingestion model is, well, it's like trying to get into a bar and you hand the bouncer your driver's license.
Okay, yeah.
The bouncer doesn't just verify your age. They now know your exact birth date, your home address, your height, and like your organ donor status. You gave them a massive payload of personal data just to prove one single fact.
That is the perfect analogy for the trust deficit. And Lynes proposes replacing that model with a concept called selective disclosure.
Okay, so following the analogy, selective disclosure is like handing your ID to a cryptographic bouncer. The bouncer scans it, and instead of seeing your address, they just see a green check mark confirming you are over 21.
Exactly. They see absolutely nothing else.
You share the mathematical proof, not the raw payload. Here's where it gets really interesting.
To build this cryptographic bouncer, Lynes details a software architecture called the LifeStack Intelligent Protection System. It is engineered as a quantum-secure AI governance platform.
Quantum secure?
Yeah, and the term quantum secure or post-quantum is critical here. It means the encryption algorithms are mathematically complex enough to resist being cracked by future quantum computers, which are expected to render our current password systems totally obsolete.
So it's future-proofing the data. What is the actual interface for this LifeStack system?
The core ingestion layer is called the Sopranus federated voice layer. It fundamentally changes how AI understands human speech.
How so?
It doesn't just transcribe your words into text. It analyzes your tone, your emotional intensity, and your cadence, mapping that underlying semantic intent into highly structured units called acoustic codons.
Acoustic codons. I think the best way to visualize an acoustic codon is to think of sheet music. The basic AI transcription is just printing out the lyrics of a song.
Right.
If the lyric is "I'm fine," the AI just reads it as fine. But the acoustic codons are the tempo, the volume, and the musical key. They prove whether the speaker was whispering "I'm fine" while crying or screaming "I'm fine" in rage.
Exactly. It captures the entire truth of the human intent.
That is fascinating.
And that multi-dimensional capture of intent transforms your voice into a cryptographically verifiable data unit. And whenever the AI accesses your data or makes a decision based on those codons, the LifeStack system triggers quantum consent playback.
Oh, I read about this in the patent. It literally generates an audible checksum tone, right?
Yes.
It's a specific, unique sound played out loud, confirming that the AI's action was just cryptographically signed and permanently recorded on an immutable ledger. It's like an audible receipt for data access.
That's exactly what it is.
So you, as the user, don't have to blindly trust a privacy policy. You physically hear the system authenticating the exact boundaries of what it is allowed to do.
It creates total physical transparency. But Lynes takes it a step further for absolute zero-trust scenarios. Let's say the AI is authorizing a massive financial transfer or executing a critical spacecraft engine burn.
The highest stakes stuff.
Right. For those actions, LifeStack relies on hardware. It utilizes the Photonic Bridge, or P4B.
So we are crossing from software code back into physical reality. How does the Photonic Bridge authenticate a command?
For ultra-secure actions, the LifeStack hardware actually fires a physical 1550 nanometer light pulse. This photon pulse is encoded with the entropy hash of the transaction.
So it's sending the code via light.
Essentially, yeah. It modulates the physical phase and amplitude of the light beam to carry the cryptographic signature. This creates a physical, tamper-evident proof of identity.
Because you simply cannot run a Python script to hack a physical particle of light.
Exactly.
If someone tries to intercept or alter the photon, the laws of quantum mechanics dictate that the light wave collapses or changes state, which instantly alerts the system to the tamper attempt. It is literally unbreakable physics.
You've summarized the hardware and the software perfectly there.
So what does this all mean? We have spent the last 15 minutes dissecting a physical spacecraft heat shield that bleeds glass and an AI trust ledger that uses sheet music codons and photonic lasers.
Yeah, that's a lot.
If you're listening, you might be wondering why we are looking at both in the exact same breath. How do these actually connect?
Well, if we connect this to the bigger picture, the grand design becomes incredibly clear. The final document on our stack is where Lynes pitches the ultimate synergy. He says, LifeStack plus ITPS equals Mars-proof AI.
The unkillable shield married to the unhackable brain.
Look at the feedback loop here. When a starship is tearing through the Martian atmosphere, the physical telemetry from the ITPS, the exact heat flux, the structural strain, the microcrack self-healing events, all of that is fed directly into the LifeStack software.
Oh, wow.
And because of LifeStack, every single piece of sensor data is codon stamped and secured with that physical photonic proof.
Meaning the telemetry data is 100% immune to being corrupted, spoofed, or hallucinated by a glitching sensor.
Exactly. The AI, whether it's Grok or another system, can safely ingest this massive stream of perfectly structured, tamper-proof data.
So it can trust what it's seeing.
Completely. It can then run predictive models on thermal erosion in real time, autonomously adjusting the flow of supercritical CO2 in the microchannels to dynamically heal the ship as it descends. The hardware protects the software from the environment, and the software protects the hardware from logical errors.
The synergy is just mind-blowing, but honestly, the scale of how Lynes achieved this might be the craziest part of the entire deep dive. He didn't just sit in a room and type this up.
No, not at all.
He claims in these documents to have built this entire architectural framework using a live multi-agent AI framework.
Yeah. He essentially built a virtual corporate boardroom. He didn't just use ChatGPT as a fancy search engine. He orchestrated a team of rival AI models to act as his engineering staff.
He acted as the human CEO and visionary. Then he instructed GPT-4o to write the underlying code base.
Right.
He had Claude 3 handle the logical structure of the patent white papers. He used Grok to model the large-scale deployment to SpaceX. And he used an AI agent called Manus, which can actually operate a computer to build the live websites and interactive wireframes.
It is a single human operating as a conductor for an orchestra of cutting-edge artificial intelligences, generating a unified patented system for interplanetary survival.
It's unbelievable.
It fundamentally redefines what a lone inventor is capable of achieving. And he's simply asking Elon Musk for a 15-minute demo to prove the entire stack works.
It's breathtaking. When you really step back and look at the incredible scope we've covered today, it emphasizes how true innovation almost always requires looking across completely isolated, siloed disciplines.
Oh, entirely.
We started in fluid dynamics and aerospace engineering, walked through materials science, and ended up deep in post-quantum cryptography and AI vocal biometrics.
It requires seeing the invisible threads connecting the physical thermodynamics of a falling rocket with the digital provenance of a database.
And for you, the listener, whether you are managing a massive engineering project at your company or just trying to protect your own personal data footprint online, there are really powerful mental models here you can adopt.
Definitely.
Like the principle of graceful degradation building systems that don't just fail catastrophically when a pump breaks, but have physical redundancies that safely power down. And selective disclosure, the deeply important idea that you should only share the exact cryptographic proof someone needs, not your entire payload of personal data.
There is one final, somewhat mind-bending detail buried deep in the LifeStack patent that really reframes everything we've talked about today regarding AI.
What's that?
It's a specific software subsystem called the Behavioral Re-Sovereignty Engine.
The behavioral re-sovereignty engine. That sounds intense.
It is. The system is designed to continuously monitor your semantic interactions, your vocal codons, and your data habits.
Okay.
If the LifeStack AI detects that external algorithm, say the recommendation algorithm on a social media feed or a highly targeted advertising network, if it detects that they are mathematically manipulating your behavior or conditioning your emotional state to keep you doom scrolling,
It actively intervenes.
it actively intervenes.
How does it intervene against another algorithm?
It issues what Lynes calls a corrective codon. This is an audible playback event, like a specific tone or prompt, designed specifically to snap you out of the algorithmic manipulation loop and consciously reassert your cognitive autonomy.
Just pause and ponder what that would actually be like in practice.
Yeah.
To live with a highly advanced artificial intelligence whose sole hard-coded purpose is to act as an immune system for your mind.
Yeah.
An AI dedicated to protecting you from being psychologically manipulated by other computers.
It's the ultimate defense mechanism for the human operating system.
Which brings us right back to where we started. Usually when we build a machine, we expect to look at it like an X-ray. We expect to understand exactly how it works and what it's doing.
Right.
But when we look at the imminent future of space travel and multi-agent artificial intelligence, suddenly that clean diagnostic X-ray isn't enough. We are dealing with systems that need to survive the absolute extremes of physics and the absolute extremes of human trust. The ultimate machine isn't just one that survives the inferno of reentry, it's the one that actively preserves your autonomy while navigating the murky waters of the future.